what it says. I start with only gravity, and I have a model for the entire universe, which incorporates most of the major features of the universe. So let's continue. I start with a simple model of the universe, an infinite lattice of identical particles in equilibrium. And these particles interact via the gravitational potential. Gravitational shielding is added to avoid the infinite forces that you would get in an infinite universe. Now, this seems a rather simple model of the universe, and actually it's an exact model of the universe. The major feature of the universe is the particles. Everything that you see, even photons, even light, is made of particles. So when I call for an infinite lattice of identical particles, those particles also contain more than 99% of the energy of the universe. So they're a very important feature of the universe. Now, for gravitational shielding, I add a term to the gravitational potential, exponent minus r over r0. That cuts down the gravitational potential interactions from particles far away, and if the particle is very far away, you don't interact with it appreciably. So because the number of particles increases as r squared, and the intensity of the interaction drops as 1 over r squared, you get a continually increasing, well, this is potential, I'm talking about the force now. You get an continually increasing force as you go further out. But this gravitational shielding will stop that, and you'll get a finite force.
We use the term fermions instead of particles? Is that
no, I would rather stay with particles.
Okay.
I'm calling these identical particles, and these particles have a mass energy, mc squared. At this point, I'm not assuming they have a spin. I'm not assuming that. The spin, I believe, applies later on in the model, after I make some more deductions.
Is there an exponential term to attenuate the field so it only has a certain finite action?
That's right, exactly. Okay, now my mode of operating is that I have to be sure that everything that I assume in this model has been observed. So I don't put anything in the model which is just merely a supposition. The expanding universe made a big mistake when it assumed that the Doppler shift caused the Hubble redshift. That was an assumption then. There was another option that you could have a gravitational cause for the Hubble redshift. That wasn't investigated, or that wasn't adopted, because there was no known method then for a gravitational causation of the Hubble redshift. But the Doppler shift effect has never been proven to be the effect that gives us the Hubble redshift. So it's an unresolved issue in the expanding universe model. So I think everyone can go along with an infinite lattice. It doesn't have to be quite infinite, but it has to be out maybe 250 billion years or so. Just the, and the identical particles, I could have assumed electrons too, but in fact the electrons turn up as a result of this model. So I want to consider first my assumption that I'm putting this up as an assumption right now, that the particles are in equilibrium, and the other assumption is the gravitational shielding. But I'm going to prove from observational data and from some logics that both of these are true.
So the gravitational shielding is the exponential term, and so why do you call it shielding?
It's shielding because you don't destroy the gravitational effect. If gravitation is a field theory, it's transferring energy to another body and causing the gravitational effect. So there's a transfer of energy there where the particle that's being attracted absorbs some energy and immediately radiates it, but in a spherical, in all directions. So the direction between the particle that's causing it, the gravitational effect is reduced. So in one direction,
this replaces the ether?
yeah, no. It causes an effect which replaces the ether. The gravitational.
I'm sure you're going to get to that.
Yes.
Okay.
The gravitational
Sorry for the
shielding, in fact, turns out to be the key to understanding the universe. You'll see why later on. So I'm going to first discuss the assumption of equilibrium. I think the best argument for an equilibrium solution of the universe is with the constancy of the fundamental constants and the laws of physics. These are observed to be constant over periods of 10 billion years and over large distances. So if you'll agree that the fundamental constants and the laws of physics are determined by the interactions between the particles in the universe, then you can see that any change in the distribution of the particles in the expanding universe, the particles would be getting further apart. You would expect a change in the fundamental constants and the laws of physics. Since we don't observe any change in the constants then the only recourse you have is to say that the universe must be unchanging. So, but now I'm going to show some observational data on galaxies, which will indicate that without doubt that the universe is static rather than expanding. First, I'll show just a picture of the extreme deep universe field. This was a picture taken of an empty space of sky where the Hubble telescope stared at a particular area for 23 days. And the galaxies in here are from z equals 1 up to a maximum of z equals 10. I just show it to indicate how do you understand such a picture? What sort of understanding can you make of it? It's very difficult to understand what's going on. Everything looks random. It's pretty, and but it's still awe-inspiring if think about it a little bit. So let's go on. I get my data from the SDSS survey. This is a survey that was begun in 2000 with the objective of measuring 1 million galaxies. And they completed this survey around 2008, 2009, but they've continued it for further objectives. So I happened to get a sample of 40,000 galaxies from this survey, which were accurately measured. And I used this to perform two important tests, and I'll show you what they are.
That looks like the interference, double split experiment.
Oh, that's just, see, they organized the SDS survey to look, or this particular pieces of data from Z equals 0.05 to Z equals 0.095. So it's a limited region in space, and it's also delineated by a cone with those angles there. You're looking up on the left-hand side, it's right ascension. It's an angle. You're looking up in a cone towards the universe. And that's why it seems flat across the top of that middle part and the bottom. Then they had auxiliary observations at a higher right ascension and a lower right ascension. That accounts for the galaxies down below and up above. So eventually they filled this in, or they did fill this in with about 1 million galaxies. So I have a very small sample of the overall, but the overall sample goes out farther in Z. This was intentionally a limited sample where you could make accurate observations and where you really did find all the galaxies in this cone. And I just show a sample of 5,000 of the 40,000 galaxies here. Okay, we'll go on and show a particular test. This is a sample of 40. Well, it's 28,000 after I eliminated some. 28,000 galaxies. I only show 5,000 here, and it's a. Let me see if I can get this. These lines represent various slopes. What happened there?
Well, actually, I was just trying to increase, maximize it.
Oh, I see.
You can see it a little better.
Okay. The abscissa is the log of 1 plus z, and the ordinate is the surface brightness of standard galaxies. When I look at these galaxies, they're correlated with between the surface brightness and the size, the radius, and also with the velocity dispersion. So you can use these correlations to establish a standard galaxy. And then you can do a least square analysis of the standard galaxy and get this black slope. This is the black slope shown there is the slope of 1 that corresponds to a static universe. The red line corresponds to the theoretical slope of the expanding universe. So you can see there's a great difference between these. The black slope should be 1, the slope of 1 in the static universe. I show it 1.02 plus or minus 0.13, 1 standard deviation. Whereas the expanding universe has a theoretical slope of 4. So this is definite evidence that the universe is actually static rather than expanding. I have to say that prior to 1990, there were no tests of whether the universe was expanding or static. After that, there are only two major tests, both run by Sandage, and he didn't definitely say that the universe was expanding. He had some weasel words in there. So The net effect is the cosmologists have never checked whether the universe is expanding. They have never done an observational test because they believe in it. They don't have to test it. And it's not in anyone's professional stature to do a test because everyone knows it's static. If you find it static, you haven't accomplished anything. I mean, if you know it's expanding, and you test it and find it expanding, you haven't done anything. So I'm the only one that goes out there and looks for data and tests it. Then I have another test which everyone will understand. Let's see. Okay. I guess you have to fix that too.
Yes, I will. This one?
Yes.
That looks good?
Yes. This is I measured the number density versus the distance. Now, in a static universe, number density will stay constant. And that's what this shows.
Okay, so, yeah, you want to the next slide?
Oh, yeah, I made a mistake.
That's okay. Hit your,
See, it's not going back.
okay, so.
You gotta kill that calendar first.
That's
Oh,
okay, I'll get rid of that.
Now we'll go
You want to
back.
go back to the graph, right?
yes. This one here.
This one here, okay.
Okay. Now, for the expanding unit, I show that the density doesn't change over a fairly large distance of about 300 billion parsecs. The density doesn't change in the static universe. And I estimate what the expanding universe should show as you get further back in time. When you're looking at far distance, you're looking at the universe when it's smaller volume, but the same number of galaxies, so the density increases. And it's a fairly large slope there, and it's very well distinguished from the black line, which is proof that the universe is static.
So your slope is the least square fit, right?
Oh, yes.
Okay.
Okay, I just want to talk just a little bit more about the equilibrium solution. Let me just say here. Well, if you have an equilibrium solution, then there's some process in the universe which is maintaining that equilibrium solution. And if you can find the processes, you have to find them, to find the process which keeps the universe in the same equilibrium state, then you essentially solve the universe. You stop there. You don't have to go further. You really do understand the universe if you find the process which keeps the universe in a stable state. You can't say that for the expanding universe because it's changing all the time. You don't have that feature, and as a result, it would be, if that was the true universe expanding, it would be much, much more difficult. This is relatively easy. And this ties in with Peter Rowland's idea about this word, what he was just discussing a little while ago. That to keep something the same, you have to have a certain process. Okay, I'll go on. That's the same. Here I'm showing a proof that gravitational shielding occurs. This is a plot of gravitational acceleration during an eclipse which happened in 1997 in China. It was a group of geologists who discovered that their laboratory was right in the path of the eclipse, the totality. So they decided to measure the acceleration on the Earth as the eclipse occurred. This is a plot of their observations, and the red line just shows a weighted running average of 11 points. And the problem was that they expected quite a different result. So they called this result anomalous, and there were very many anomalies in these observations. Of course, they were only anomalies that you didn't understand what was happening.
Could you say what is, it's hard to read, what is plotted versus what?
What is that?
What is the abscissa ordinate?
Okay, the abscissa on the bottom.
I did that, I just wanted
Okay.
to max.
It's minutes after local midnight, a very strange arrangement, but that's what you need in this particular thing. So they used a very precise gravimeter to measure this, which is accurate to 1 part in 10 to the 6th of centimeters per second squared.
What's
That's
the
1
order?
billionth of
What's
the
the ordinate?
gravitational field that we're standing in now. What's that?
What's the vertical?
Oh, the ordinate is the acceleration in 10 to the minus 6 centimeters per second squared. So that's a millionth of a centimeter per second squared. Very accurate.
So it's a very tiny effect.
Yes. If the moon had been half as large as it is now, I wouldn't have been able to present this model of gravitation. You need a big piece of apparatus to measure this gravitational shielding. And this is the biggest model I could find.
Why are there two dips? It's gravity.
That's the anomaly. Let me say one other thing. This only shows part of the data. When they set it up, they started the gravimeter 1 week before and 1 week after. I don't show those results. They stayed very, very close to the 0 mark there. There's nothing going on. Now, all of this data has first been corrected for tidal effects because they're 200 times greater than the effects we're looking for. But they have a method of calculating to 1 part, 10 to the minus 6 centimeters per second squared, as a matter of routine, geologists. So let's see what we can say about these anomalies. There's 3 things happening here, and you have to remember that. First, the moon's shadow is moving from left to right in this diagram at 50 kilometers per minute. Second, the gravimeter, which is recording this data, is located, let me see, about here, right in the middle of this group of things. Okay. And the third thing is that this apparatus to measure the gravity is sitting on the crust of the Earth, specifically one of the plates. And the plate is moving under the reduced gravity of the sun. So the plate is falling. And you see here, the plate is falling at 6 times.
Actually, what happened is that you went back to the previous slide.
Oh,
I'll go
no, I
back.
didn't touch that, right?
When you click that button, that's what happened.
Okay.
It's okay.
Okay, On the left-hand side here, this is down at 5.9 times 10 to the minus 6. That's a negative acceleration. The gravimeter is sitting on this plate and it's falling at that acceleration. And that's what it's measuring. And the same thing for the dip after it. This dip after it. That's another, after the acceleration, after this horizontal part there, it goes through the same thing again. And the reason why you see that is because the gravimeter here is not under the influence of the shielding of the moon, and therefore is measuring just the well, I don't know.
Well, when you click, it goes to the next slide.
Yeah, there we go. Okay.
Yeah, Rick,
Yeah.
that pointer sometimes.
Okay. So, but when the moon is in this position, when the shadow of the moon is right over this, there's a shielding effect. The sun's gravity looks like it's about 20 times 10 to the minus 6 centimeters per second squared less. And this, the important point to note is that this gravimeter is also falling free at that acceleration, and so it doesn't feel the acceleration. If you're in an elevator and it's accelerating downward, for a short time you feel lighter because you can't feel that deceleration. You're accelerating in the Earth's gravity and you can't feel it. That's just like the whole Earth is in a free fall. We can never feel the gravity of the sun because we're in a free fall. We can't measure it. So this solid, this straight part here is the gravitational footprint. That even though it's in the field, gee, this is not designed very well.
It's okay.
So this part here is the gravitational footprint, and it's interesting to note that this is about 3,000 miles across. That's equivalent to the optical. The optical total is only 100 or 200 miles. So why is the gravitational one? The question is, why is the gravitational one 3,000 miles across and the optical only 50 or 100? Because they're different effects. The optical is just looking at the surface of the sun, whereas this is looking at the whole volume of the sun. And you know from Newton that the gravitational vector from the sun originates at the center of the sun. So that gravitational vector sweeps over this 3,000 mile area and produces this flat portion. So that explains this diagram. And from the diagram, I get this gravitational shielding of about 6 from this. I'm also able to predict what this is from a field theory of gravity. So this corroborates that gravitational shielding is a real effect. And this is the first corroboration. It's the first corroboration. They've had many tests before, but they could never say that gravitational shielding occurred. And even the ones who made this measurement, they couldn't say that gravitational shielding occurred because they didn't understand these anomalies. So I'm the first one to understand these anomalies and therefore analyze it and discover that gravitational shielding is
The anomalies are the big dips. The effect is not the slightly lower center portion, right? The
No,
effect
they're
is
both, in
What's
fact,
the effect is that the center portion is slightly lower?
well, the center part is slightly lower because this is affecting the whole Earth too, to a small extent. And you're getting a falling of the Earth also, but it's very small because the beam is not intersecting the whole Earth.
But what are the big, that's what is happening when the big dips occur?
When the big dips, you have the gravimeter located at this position. And when these dips are occurring, the gravimeter is not in the beam of reduced acceleration. So it's just measuring the plate falling. The plate is actually falling over here before it gets to this point, and it's falling all through this region here. But the gravimeter is just registering the falling of the plate, the acceleration of the plate down. Does that clear it up?
Somewhat.
It's all and when the shadow of the eclipse is here, this gravimeter is falling like in an elevator, and it doesn't feel this reduced acceleration of the sun. So it's a combination of free falling and not being in the region where the free fall occurs. Now there was a paper that came out on this to analyze the situation about 1 or 2 years afterwards. There's three people who were in gravitational physics. And in their paper they said gravitational shielding did not occur because of these anomalies. They couldn't understand these anomalies. So they essentially stopped all research on this problem because they said the last word. So the import of this is that gravitational shielding is a real effect. It's exactly the same, right magnitude to gravitationally to do gravitational shielding in the universe. This shielding actually gives you the Hubble redshift. So I think we can go on and discuss some other portions.
You want to go to the next slide?
Yeah. Okay. This just gives you an idea of how you calculate the potential of a particle in the universe. Pick any particle and you can do this calculation. It's rather simple. Under the integral sign there, you see I'm sorry.
That's okay. We'll go back.
I'm not doing
Yeah,
this.
keep going back to page 8, I think.
Okay. The R exponent minus R over R0, you integrate that. The R there, it means that the R is equal to R squared over R. R squared because the number of galaxies would increase as R squared. And you're dividing by the potential R, so you have R there. And this gives you minus CR R0 squared, and if you calculate C or use C and R0 values in there, this comes out very close to minus MC squared. So in effect, it's very close, or actually showing that the energy in the universe is 0. And I've assumed, I haven't mentioned it before, but I assume that there is no input of energy or output of energy from the universe. So any energy in the universe has to be sort of manufactured. So let's go on a little bit further. I'm just showing that something that's very well known, non-relativistic energy of a particle. And it's made up of the mc squared, which is the mass energy, the potential, which we just calculated, kinetic energy. Kinetic energy can be ignored in this because it's very small. And this equals the constant. It's just an equation for the conservation of energy.
10 minutes.
10 minutes? But what determines the particle's energy, mc squared, and why do particles exist? We want to find out that. There must be an important reason because particles are ubiquitous in the universe. They're the only thing in the universe. Okay, to answer these questions, I expand the potential in a Taylor series. Now, little definitions just to show some of the conventions I use. The position of the nth particle is nd plus yn. Yn is a small perturbation in the distance because I'm going to check the universe for small changes. And from the small changes, maybe I can deduce the processes which operate in the universe to maintain the equilibrium universe. And once I find those processes, I can legitimately say that I understand the universe. So let's go. And then the distance between the nth particle and the nth plus qth particle. I'm assuming long-range interactions. So every particle interacts with every other particle in the universe. And you need some sort of nomenclature to describe this accurately. So here's the Taylor series for a pair of particles. What I'm doing is supposing that there are small perturbations in the movement of the particle. They're not completely stationary. And I want to examine what that effect has on the potential. Now this is for a one-dimensional arrangement of particles. So I changed to a spherical location of particles. So I just say the number of particles increases as r squared, and then the p's there. You see p and p prime and p second. Those are the derivatives of the potential function. So they become functions of r, and their values are determined by an integration over all the particles in the universe. So this is, if we're talking about all the particles in the universe, this is a representation of that. I have that sum sign for the first two lines. The top one is for the first two lines, and the summation further on is for the last two lines. I have to break it up like this because if you have a particle here, it's acted upon by a hemisphere of particles on this side and a hemisphere of particles on that side. So the particles the particle, say for the normal Newtonian force, it's acted upon by equal forces in opposite directions, so the force cancels in a homogeneous universe. Let's go on a little bit. But it has to be broken up like this. So we're calculating now the force on the particle P. This is what we're aiming at in this Taylor series expansion. So we differentiate the potential with respect to the movement of a single particle. So we'll get the force on a single particle that it sees when it moves a certain distance. And you see down here, yeah. Let's see. Okay, here. And you see down here, I have P prime R and minus P prime R. Those cancel, and you're just left with the sum of these two terms. And I'll show you what that looks like. Here's the force, and it's due to these terms here times the P second. And if you calculate what this looks like, assuming a wave representation, you get this single term here as the result, as the force acting on that particle. So this is summation. You're summing over all particles. And if we go on, one thing I want to say right now is the first PR that we were talking about gives you the potential, the ordinary potential of any particle. Second gives you Newton's gravitational force. And it turns out with the gravitational shielding that it's zero. You don't, the Newton's force is zero in a equilibrium universe. And the only force is a tidal-like force, and it's also a restoring force. It's a constant. Now, this restoring force comes into the play when you consider how light traverses, propagates in an empty space. The previous theory of it was that there was a medium, an ether, but that's been disproved. So there was nothing replacing that method. What you need for a wave to propagate is a restoring force. If you move the particle a certain distance, there should be a force appear which pulls the particle back. It accelerates. It keeps on accelerating in the other direction, but it's being pulled back. And there's inertia force involved there, and you get a vibration. So the gravitational shielding has introduced this restoring force. If you do this for an ordinary static universe without gravitational shielding, this last term here, the P second, equals zero. You get no restoring force in a static universe without the gravitational shielding term. So you really have nothing if you don't have gravitational shielding. You don't have a universe. Okay. Here I'm going to assume a wave solution. I'm putting the force equal to mass times acceleration, and I just assume the derivative location, d squared yp dt squared for the acceleration. And then I calculate the frequency in the next two terms. Now I get a frequency of 10 to the minus 18 hertz. This is a vibration, an underlying vibration in the universe with a wavelength, the length of the universe, or the size, the mean length, mean size of the universe. The interesting thing here is 10 to the 80th of these vibrations, 10 to the 80th modes. One mode occurs for every particle in the interacting part of the universe. And you'll see what happens. We're going to, well, we don't have to assume, but we'll add up the number of interference terms that you can get from those individual, if you have a general solution of a wave equation, you can add up the amplitudes. And if the frequency is the same, the frequency of those modes are all the same, if the frequencies of the waves are the same, you keep that frequency. But you have all of these amplitudes added up and squared. And it turns out that there are n squared terms that result. Oh, here we are.
Correct.
See here, n a squared. This is the term which gives you the elementary particles. But over here, you have the cross product terms. Yes, 2 minutes. Okay, I'm almost done. You have the cross product terms, and there are 10 to the 160th terms there. Now, what this leads to is, in the universe, you have three different forces. The ordinary gravitational force, which is very small. Then you have another force which gives you the elementary particles, which is 10 to the 80th times stronger. And then finally, for the cross terms here, you have a force which is 10 to the 160 times stronger than the gravitational force. You have these three forces that occur in the universe. Let's go. See, I'm saying I'm adding together 10 to the, I say 81, 10 to the 80th wave amplitudes. The combined wave mode still has the same frequency. The squared terms form the elementary particles by Bragg diffraction. So you have an underlying wave system which has a very low frequency and a very large wavelength, but by the time you add them all together and do the Bragg diffraction, this forms particles which are 10 to the minus 13 in size and have a mass energy of 10 to the minus 3 Earths. This is the origin of the elementary particles through a Bragg diffraction process. And the cross product terms determine the splitting of the identical particles and the electrostatic force. It turns out that the electron and the proton are the same particle, but they're split by the very large interaction forces of the cross product terms. And you also get the electrostatic force out of this, and also the plus and minus terms of the electrostatic force. And you can go, well, let me go a little bit further here. Here's a two-state model of identical particles, and here's a quantum two-state equation. And you can apply this to the particles. These would, the H11 and the H22 would be the identical particles. And then you would have this, I'm using an approximate two-state model now. And the H12 and the H21 is the cross product interaction terms. They're very large. And in this approximate model, these interactions are reduced as the H11 and the H22 begin to differ, because the interaction pushes one up and one down. And the further you push them apart, you reduce the overall interaction until it equals the energy of the lower one, and then you have an equilibrium situation, have a solution. And you can show that this gives you the mass ratio of the proton and the electron, 1836.
I got the 13 upstairs. Cross gave the same.
So I'll go on a little bit further.
Yeah, that's black.
Oh, here's the Hubble redshift. First I show the definition of the Hubble redshift, and then I equate the observed potential and the gravitational potential. The 1/1 plus c is a measure of the gravitation. It's the observed gravitation potential. And the exponent minus r of r0 is the gravitational potential from the gravitational shielding, and you solve these and you get Z, equation for Z, and equation for R. And this is a very accurate calculation of the parameters. Okay, we're still going. Oh, speculations. Net energy of the universe equals 0. So you have to have some origination of the internal energy. It's either from the 0-point energy wave modes or the Laplace equation. And I show the Laplace equation down here, and you note that the Laplace equation has a solution in spherical coordinates, which is P equals 1 over R. I will go on a little further. Since solutions of the Laplace equation represent the smoothest functions possible on a space, the potential energy PR equals 1 over R should physically occur. Also, the universe may be just a physical realization of the infinite number of solutions of the Laplace equation. So that's my talk.
Thank you, Tom.
Now, everyone should understand